Welcome to my talk, 7 Vulns in 7 days, where we're going to be breaking bloatware faster than it's been built. To start this, I need to tell you a story of where I'm playing games. It's summer holiday back in South Africa. I'm taking some time out and playing my favorite game. At the end of that session, though, I notice at the bottom right, Asus DriverHub is asking me to install a driver update. A little confused by this, I click it, and a browser opens up. This driverhub.asus.com is in a browser, and it's asking me for more things to install. This is fairly confusing, but I continue with the progress. Eventually, a modal pops up asking me to restart now. Now, I've already been a little suspicious by this point, but I've been really suspicious right now. How could this be working? The installation completed and I need to reboot? Is there some cloud-related thing here that I need to consider? I'm not really sure yet. So I go back to DriverHub and I click that Reboot Now button. The reboot happens instantly. There's no cloud involved. I have an okay internet connection, but the speed at which this happened was fairly confusing. Anyways, my computer comes back and I quickly pop open the dev tools and I realize there's a local web server running on my computer with which this DriverHub website is interacting. It's also the end of my holiday now because I decided I'm going to take this journey that I'm going to tell you about right now. So, thank you for coming to my talk. My name is leonjza. I'm from South Africa and I work for a company called Orange Cyber Defense, more specifically in their SensePost team. You can find me online. I'm leonjza, basically everywhere. And I do like research, hacking, and building stuff. Today, I'm going to tell you this story about hacking bloatware and a whole bunch of vulnerabilities that I found. We're going to look at 4 products, which include Asus DriverHub, MSI Center, Acer Control Center, and Razer Synapse 4. All of these vulns have been fixed, so if you update to the latest versions of this stuff, you'll be fine. At the end of all of that, we'll have some sort of conclusion and talk about what all of this means. I need to prefix some of this talk. There's going to be a whole bunch of tools that you're going to see, like the list on the left, and we're going to look at a whole bunch of code snippets. I've tried my best to sort of isolate the bits that you need to look at, but keep in mind that it's going to be quite fast-paced, so pay attention. The first product to look at will be this Acer DriverHub and the 2 CVEs that I found in that. When you look at these processes, one of the really useful tools you can use is called Process Explorer. And specific to Asus DriverHub, when you look at what backs that program, there are 2 processes, this adu.exe and Asus DriverHub.exe. And more interestingly, adu.exe listens on a TCP socket, so things can connect to it. Now at this point, I'm looking at these things on my home PC where I play games, but I realize if I want to do some research, I want to install this in a virtual machine. Thankfully, as to no one's surprise, when you install Asus DriverHub in a VM, it goes, this is not an Asus product. It's not wrong. So we needed to do a little bit of work to get that going. Opening the installer in something like Binary Ninja, it has this really nice feature where you can take some code and patch out a branch. Maybe you want to invert the code flow or do something else with it. It's fairly simple. So with the installer, I do exactly that, really with the point being so that I can get a successful installation in my Parallels VM. With that installed, I can finally open DriverHub in this VM. And again, the VM is handy. I can snapshot, roll back, do all the kinds of things without it being a pain. But when I open it up, again, it tells me this is not an Asus product. Can't fault them, they're right. But when you open burp and sort of see what the requests look like when you open Asus DriverHub, you quickly realize there's an initialize call where the local web server responds with this is a supported product or not. Because this is burp, I can very easily change a false to true, and suddenly my product is supported in my VM. I didn't get all the fancy driver updates. I could install the Armory crate, but that was good enough premise for me to start playing around with this stuff. I've mentioned this before, there were 2 interesting processes, and for this part, we're focusing specifically on adu.exe because that's the one that has the TCP socket that it was listening on. Opening up adu.exe and something like Binary Ninja, you'll see a whole bunch of features that this has. Of course, the web server was of interest of me, so when doing some string searches, you can find endpoints that look like HTTP endpoints that you could call. One of those is this reboot endpoint, which is really patient 0, what I was working with. Following the flow in how is the reboot implemented, you'll end up in a code piece that will look something like this. Really, the interesting part is the call to exit Windows, which will exit Windows. To visualize what we know so far, we can quickly have a look at how this would work. Imagine a browser where you're browsing to driverhub.asus.com. When that page loads, a JavaScript fetch request is made to a local web server, which then in native code makes a Win32 API call to exit Windows and reboots your computer. I wanted to create a small testing harness for this, so I wrote some PowerShell to sort of replicate this reboot feature. I make a web request that looks something like this, and the first response I get was an access denied. Now, one thing that's really interesting when you look at these things, they often emit an insane amount of logs. Logs are really handy for developers, but they're also handy if you don't really know how the software is structured. In the case of Asus DriverHub, exactly the same thing is true. There is a log file with a random name that they use, but it's quite useful in telling you what's wrong. In this case, I can see there seems to be some origin-related error, where the origin that I passed along was not allowed. In fact, I didn't pass one. So I modify my test harness, add the origin of driverhub.asus.com, and I get a new error. And everyone knows when you get a new error, that's a sign of progress, which is great. Looking at the logs, I can now see the origin is allowed, but the body is empty. So I clearly need to send some content along to actually invoke this reboot. But keep in mind that driverhub.asus.com lives in a browser. So we can open the console and inspect the JavaScript that's being used to speak to that local web server and get a sense of what parameters might be used. In this case over here, you finally, between this minified mess, as you would expect, find a post request that gives you an idea of what the structure looks like for that web server. If I take that knowledge and update my small test harness, it would look something like this. And I'm finally at a place where I can also reboot my computer. Totally unnecessary, but this is a good harness for me to play with. Cool. With understanding that, let's move on into the first bug, and it's something that I'm just going to call the string contains bug. And to understand the string contains bug, we first need to understand how origin header validation is supposed to work. Imagine for a moment two tabs where one is driverhub.asus.com and the other is driverhub.notasus.com. Both of these tabs, both of these domains serve hypothetically exactly the same content. There's no difference but the domain from which you're using to browse to the content. When the page loads and you might want to invoke the reboot feature, a fetch request will be made to the reboot endpoint, after which, as a security mechanism by the browser, an origin header gets attached. This is a way for the web server on the other end to kind of know where this request came from. And how DriverHub implemented this as a security feature, when it is not asus.com, the request will fail. It's where the access denied originally comes from. Now, the challenge is while reversing this stuff, I often sort of rename symbols and sort of try and figure out if I have a rough idea of what a function does, I'll give it a name with a question mark. And in this scenario here, I think the function I found here was a string contains function. Question mark was, I think. But I noticed an invocation that included this .asus.com argument. Diving into string contains, you can see there's a memCompare call that has an iterator to sort of compare the input arguments over what the iterator is. To visualize this, it can look something like this. Imagine you're going to driverhub.asus.com and it wants to know if this is the asus.com origin where you're at. Using the iterator, it will check the string for 9 bytes exactly until it goes, okay, this looks like asus.com is where this origin came from. However, because this is a string contains, if you pass something like driverhub.asus.com, the same effect will occur, except it will actually stop the moment .asus.com is met, meaning any origin really can be used for you to make a request. So that's okay. Take my test harness, and you see that I can do exactly the kind of reboot with the wrong origin. Now, you may have come to this talk for a vulnerability, but I'm really just showing you how to reboot your friend's computer. But no. More importantly, you can now use an arbitrary origin as long as it contains .asus.com and interact with this local web server that DriverHub gives you. Now, rebooting is fun, but what's more interesting is gaining RCE. You might remember from a previous slide that there were a whole bunch of endpoints that we could look at. There are many other ones that are interesting here, but one we'll focus on right now is the update app endpoint. Just like reboot, we can find the post body that update app wants, and it looks something like this. Focus on the URL element for a moment, and we can try and pass a full URL to an exe, sort of test what this thing does. Like if I give it a URL, will it download? We update our test harness with exactly that URL path that we give, invoke the request, and if we inspect the log files, we see a line that tells us this agent URL can't find .asus.com in it. Well, I showed you the string contains bug, so exactly the same vulnerability exists here, where you can just give it a URL to any origin, as long as .asus.com exists, and it would download that, which is quite handy. The challenge, though, is when you run it, continue looking at our log files, we get a new error, the universal indicator of progress. It tells us that this one is not signed, this executable that we've sent. But the progress here is our content has downloaded. Of course, the reverse engineering journey continues, and we finally have a look at what the PE signature validation looks like. And you see a line like this. Does one of the properties contain Asus Tech Computer Inc.? Doesn't really check if the cert is valid. Thankfully, tooling already exists that lets us clone PE signatures from a valid binary to whatever we want. Critically, the signature won't be valid, but the properties exist, which Asus would then be happy with. So I want to show you a very quick demo of what this would look like, putting these things together and sort of getting remote code execution with one click. What you're going to see now on the left-hand side is a web browser of your victim. Somehow you've coerced someone to browse to your website. A website that has .asus.com in the URL, a subdomain, whatever you have. On the right-hand side is just a little bit of showing what's happening. We'll tail the log files of adu.exe to see the progress of that process. So on the left, on the right, we start tailing the log files. On the left, I go to my domain, browse to my fancy website, and we pop calc with one click. What's really interesting about this setup, though, is none of the components of Asus DriverHub runs in an elevated context. They're all normal user processes that run. However, you can imagine most gamers, they're probably an admin on their computer, but they have a UAC setting where they'll need to at least click accept or deny. It turns out, if you have a side-by-side assembly manifest, or what seems to be known as a UAC manifest, that you apply to your target payload, this entire process actually bypasses the UAC prompt as well. So if you're an admin, this code execution actually turns code execution in an elevated context. Now, Windows has some heuristics to sort of determine, and this is an installer-based thing, should I run elevated or not? But the way to make this deterministic is to actually implement attach an XML like this, which has this requested execution level field. With this XML at hand, you can run a tool called mt.exe, which you'll get with Visual Studio, pass it the manifest and your target executable, and it'll look something like what you've probably have seen before, that sort of signature yellow, blue shield that it has on top of it, indicating that when you run this, it might run in an elevated context. So for exactly the same exploit, if you pass along a exe that you've added this manifest to, that code execution will turn into an elevated code execution, bypassing UAC. Talking about a impact for this, when I looked at my motherboard that started all of this, there's this handy, I wondered, where did this come from? You look at the BIOS, and there's this line that says you can download and install Asus DriverHub automatically. When I found these vulnerabilities, I disabled that fairly quickly. But that should give you an idea how some of the software might actually end up on people's computers in the first place. Okay, so that's Asus DriverHub. So let's look at a quick summary. It could be an alternative way to reboot your friend's computer, or a way to execute arbitrary code. It can auto-install itself based on this BIOS setting, but really it's the sort of misuse of this strange RPC mechanism. How you invoke those HTTP requests is not great. The Chrome working group actually has a spec proposal which should gate access to local resources, similar to how webcams and microphones would be gated today. So what it really implies is they're proposing that a little pop-up comes up saying, hey, this website wants to speak to something on the local network, which sounds like a handy thing. And I think, a little bit to no one's surprise, the disclosure was a little messy. I'll get back to that a little bit later. Now I'm still on my holiday. I'm a little excited. I found some really cool vulnerabilities. I'm going to tell Asus about this, and that's nice. I've disabled this stuff so that no one else exploits me. But I did have a moment and wonder, what are other vendors doing? If this is one not small vendor, what other things can we see? So I Googled around for products, companies that do similar things, and unfortunately I come across MSI Center next. The thing with MSI Center, though, once you install it, like in my VM, it has this pop up this display that says, for you to use this, you need to add your local user to the administrators group. It's a little confusing to me because all of the processes that run in the backend already run in an elevated context. So I'm not sure of why my user needs to be admin already. But much like Asus DriverHub, it also has a component that has a local TCP socket that listens for connections. The difference, though, in this case, is actually elevated as well. Because this is a TCP socket and I don't really know what it looks like, I open the client and Wireshark to see what the connection between a client and that elevated service would look like. And you would see some output that looks like this. It's a binary protocol that goes in, but the bits that come out seem to be JSON. And it's familiar, but not entirely. The nice thing, though, because the MSI Center client is written in .NET, the reversing of this is fairly easy. There's no obfuscation or anything like that, so it's a little bit like looking at a source code review from that perspective. Anyways, when you go through this code a little bit, 4 interesting things come out. There's a launch server method that does some housekeeping, makes sure the port's available, etc. Then registers 2 callbacks, where code runs when a new connection comes in, and code that runs when data is read into that connection. But finally, and probably the most important part, is this data response function that takes a structure of the data that came in on the socket and hands it off to other components. And we'll talk about that in a bit. One of the ways in which the software knows where things should go is these definitions, sort of static byte structures of features that it supports. Here's an example of a reboot and an uninstall function, but many components in this bloatware has different definitions, which you can see an example of here. With those byte structures defined, there is this sort of very primitive compare bytes call that sort of figures out, based on how all of the features that the software supports, when does which block run. And that would look something like this for the reboot case. A more complete example, you'll actually see 2 distinct things here. One is a plugin loader, which we'll get to in a second. But in this case, for reboots, it actually finally does the reboot by running shutdown.exe as an outcome of this thing. So what we're really saying is we just have a TCP connection that we can make to the service and send through the bytes for these commands to make it do something. So I did exactly that, but when I sent this along, nothing happens. Referring back a little to the Wireshark output that I was looking at, I realized that I didn't know yet what those first 4 bytes were for. The bits afterwards started looking familiar to commands that are implemented in this bloatware, but the first bytes I wasn't too sure of. But regardless, at this point, I don't really know what it means yet, and you sort of YOLO it. Add the 4 bytes to your POC, send it on, and your computer reboots again. Now, this might be a talk, 7 ways to reboot your computer, but no. More importantly, we now have the primitive where we can interact with the privileged process from a non-privileged context. Now, before we get into the bugs, I do want to talk a little bit about MSI Center's software architecture, because I think that is quite interesting. When MSI Center boots up, it has this idea of a component loader. It scans the program files directory for any DLL that matches this API_*DLL format, tries and loads it, kicking off an initializer that would register that DLL as a component that contains commands. Practically what it means is you end up with this sort of component command map. Every component has a unique ID, and each one of those components implement unique commands. And mapping that to the TCP protocol, it means every TCP frame defines the component it wants to target with those first 4 bytes, and then which of those commands that it wants to run. More crucially, with the component loader, and you'll remember this from the plugin loader earlier, there's this piece of code that gets to this transfer command part, which tries to find the component that is loaded and sends it off to that plugin. Really just hoping that plugin knows what to do with it. Okay, so let's look at the first bug, which is a local privilege escalation in this MSI Center. One of those commands that exist within the MSI Central Server component is called command auto update SDK. And you can see it accepts 2 arguments. One is a target program and arguments for it. Now, I think you know where this is going. More importantly, when that command is invoked, the target you want to run, let's say there's an executable on your desktop, gets copied to C Windows temp, MSI Center SDK. Some verification work, which we'll talk about in a bit, happens, but eventually this execute task function runs, which schedules an immediate scheduled task, that's a mouthful, to run that executable and any arguments, and if isSupervisor is set as true, which is the default, it runs as system. The part before that happens, though, is a code signing check that actually checks if this thing that I'm trying to run is actually signed by MSI. I don't have an MSI code signing cert, so naturally I can't pass this check. And the right way to do it is with the win-verify trust call, which they do in native code. So that was a bit of a bummer. And it leaves me with this sort of sad holiday vibes that it's also the end of the holiday and I don't have a cool vulnerability. Until I realized, hold on, I need to relook at this thing. There is something to look at. So if we revisit this auto command SDK, auto update SDK command, and break it down, the first step is to copy the target we want to run. So if we take prog.exe, the software will copy that to MSI Center SDK and the Windows temp directory. It would then do the verification. And verification is running win-verify trust over that target file that got written to the temp file, to the Windows temp directory. If the win-verify trust passes, the scheduled task is executed, which is really just saying run that MSI Center SDK as system. Because it's fairly quick, eventually the scheduled task will run it, and which again will be a system. But the challenge here is the one that got verified and the one that got run isn't bound in any way, which gives us this opportunity for a race condition that we could exploit. Taking copy target and imagining we run it at two exactly same times, one might be pwn.exe, another could be this, I don't know what MSI toast server.exe does, but it was useful because it had a valid signature. If we run both of those at the same time and it copies it to the same directory, which one of these two is the scheduled task going to run? And if we do it really quickly, there's an opportunity to run the wrong one. So my exploit plan here is to race to execute with two threads. One for this legitimate MSI toast server thing, did nothing, but it was handy for its cert. And the second is then for my payload, which I was using to just add users to the local system. The end means that that scheduled task would be confused about which one to run because there's no binding to who got verified here. So if we take a look at a quick demo of what this privilege escalation might look like, it would be something like this. At the back is MSI Center server running. Just to show the context, I start by checking that I don't have an MSI user and I try and add it. It's really just to indicate that I don't have access to do that right now. I then run my POC, which takes an executable, which is not signed, and adds a user. Once the race is won, I can double check, and I now have a new user, which is also an administrator, added to the local box. That's a very complicated exploit, though, because LPE2 is significantly simpler. Continuing this process of learning of which commands exist, there's one that lives in API support, the DLL, also has an execute task routine, but the difference here is it was its own implementation of execute task. It matches the function prototype, but none of the security features that existed in this common lib. And you can see probably the developers wanted to get everyone to use the same library, but someone decided not to, or there's some legacy code, I don't know. But what is nice about this re-implementation is there's literally zero verification. You pass the target, it schedules the task, and it runs. So my exploit now becomes sort of 4 lines. I give it the task, and we get local privilege escalation. It's fairly silly. Okay, so in summary, for the MSI Center, I don't have there's another way to reboot a computer if that's what you're into, but more importantly, code execution in a privileged context. Comes pre-installed when you buy a laptop for many of these laptops, but it's yet another example of this sort of RPC mechanism that gets misused or is not well implemented. It's a bit of a depressing outcome, but I sort of continue, sort of day 3, day 4 of my hacking rampage, and Acer Control Center unfortunately comes on my radar. Acer decided to squish 2 bugs into 1 CVE, but that's fine. So let's take a closer look at that. When you install it, if I recall, this one doesn't do any verification. It's happy to run on my Parallels VM. But when you look under the hood, you'll see that there isn't really a TCP service that we can target, but instead it's a named pipe. However, one of the services, or the privileged services, one of those services is privileged, which makes it an interesting target. If you reverse some of this stuff and you sort of get an idea on how this software is put together, you'll see there's really 2 components, which is very classic client-server architecture. There's this native binary running as a service in an elevated context, and then there's this normal user client that you would run, but that's written in .NET. And you can already see which one of those 2 would be easier to reverse. Because a named pipe exists, that's sort of the mechanism in which these 2 can connect. Taking a look at the client, one of the functions that you find that's very interesting is called send command by name pipe. It takes the pipe, a 7, a target path, and 113. When you look at this in a bigger picture, when that gets sent over to the native binary, somewhere in some of the logic over there, which you reverse, there's eventually a create process as user call with exactly that target that you've given it. So it's such a silly, like connect to the name pipe, pass a target, run thing, that really for the demo, I just sort of give you a screenshot over here. The interesting part is coming. But what's nice about this is there was some encoding that I could just rip out of the Acer Control Center client, implement it in a small.NET program, give it a path, and it would run. But the first thing that confused me here, though, is this service is running in an elevated context, and my notepad was not. Like I was only getting low code execution as a lower privileged user. And I wasn't too sure what was going on there yet. Regardless, moving on to the name pipe, I sort of look at the access and I realize it has this file all access thing, which is something you explicitly need to get wrong. Like you need to go set that. This is not the default, which means although it's not a low privilege escalation, a local privilege escalation, it's actually remote code execution. So I can run Notepad on your friend's computer. So if we take a look at a quick demo, let's see what that looks like. On the left-hand side, I have an attacker VM. It's not connected to any domain or anything interesting. And on the right-hand side, there's a user running Acer Control Center. I have a quick look at what the IP config is between the two. And when that is done, I run my POC, which connects to the remote end and asks it to spawn Notepad over that name pipe. I like remote code execution, but I don't like not understanding why it wasn't as a system. And so I still had some questions remaining. Why is this system thing happening? What is that 113 that I've got that I'm sending along with the argument? And if assuming 7 is a command, what other commands exist? Continuing looking at the server side, elevated binary, eventually you find the other commands that exist there. I had this weird pointer matching thing to invoke them, but regardless, they'll look something like this. None of the functions that I could see in the Acer Control Center client would invoke any of these other functions. So I sort of left to a place where I needed to manually build my client, invoke command 6543, and get a sense of what the arguments would look like and how they would get invoked. To use that, I use my favorite tool called Frida, which I really like, just to get a sense at runtime, what does the invocation look like and which code paths finally trigger that. The unfortunate thing, sadly, comes along, none of those code paths seem to be doing anything interesting. In fact, it was just a bunch of registry read and writes, etc. So I revisit that run command function where I have a path and I have this 113 that comes in. I'm a few days into this reversing process and I started realizing the fatigue sinks in, but thankfully I had a closer look. One section of this function has a specific condition for that argument that takes the 113. In fact, when you make it 114, in fact, incremented by 1, you might notice that x3000 matches a constant when you look at the Windows SDK to have a SID initialized for a higher integrity process. So when this initialized SID function finishes, a token gets built and that gets used to run the target process. What that really means is when you have 113, it runs as a normal user. When you make it 114, it'll run in the elevated context. So change send command by name pipe, making 113, 114, and you now have a elevated command execute or an LPE on that system. The really neat thing, because of the broken name pipe permissions, this will work remotely as well. Okay, so in summary for the Acer Control Center, while I don't have another reboot POC for you, you have the ability to execute code in the elevated context on the other end. This is also pre-installed on a whole bunch of laptops. And while it's not a TCP service, it's sort of the same thing when the name pipe is configured like that. So you definitely want to avoid that if you're doing that stuff. Okay, the last target that I want to talk about is Razer Synapse 4, which also has the CVE. When you install Razer Synapse, it's their newer version of their product. 3 has been out for a while, but this one is not too old yet. It'll look something like this when you're installed. I don't own any Razer products, so the menus and things are empty, but that's fine. For one moment though, when you look at what's happening under the hood, you need to appreciate the amount of processes that's running here for when you probably want to change the RGB on your product. I don't think it's necessary for that much, but this is not my domain. Regardless, the keen-eyed here may have already noticed the process that's got the name and what's about to happen, the Razer Elevation Service. It runs a system, and this is an interesting target. The challenge with it, though, is it doesn't, unlike the previous targets, there's no listening ports or name pipes or anything like that. It's written in C++, which makes the reversing a little bit more challenging. And so this target seemed a little hard at first. Attach Procmon to it, and I interact with it using that Electron client. Eventually, I could get an interaction with the Razer Elevation service when I installed another component, this Razer Chroma thing. I don't know what that is, but the installation triggered the code path. And as at this point, I realized I needed to reverse that client to see how exactly this code execution works. Because it's an Electron app, the sources will be bundled in what's called an Acer archive, and the Node team kindly maintains a tool that lets you extract these, which really just mean you can end up with the JavaScript source code of that Electron application when you run this tool. I like reading source code to find vulnerabilities, so this is incredibly handy. When you dig into the detail, you'll find that they're doing what's called a foreign function interface using this Node FFI library. In fact, it looks like a private fork of a public tool that they're using here, so you can see the changes that they have made. But to understand how this works, what really happens is in the JavaScript Node world, you can call a function like simple service initialize here, and the Node FFI library takes care of all the translation and loading of native code to make the same function call. It's a very nice abstraction layer. It also supports multi-platform, multi-architecture, so Node FFI will take care of is it x86, is it Mac, whatever you are running for, and just call that native code in the end. What this looks like in the Razer Synapse app is you'll have a definition, client-side, which when I looked at this the first time, I thought this was Frida. The first time I'm seeing Frida use non-reversing case. But it's really a simple definition of what those function calls would look like in the native world. To double check that, you open the simple service DLL that they're using in Binary Ninja or your favorite reversing tool, look at the exports, and you can clearly see the matching between the two. So using this foreign function interface, they're calling a DLL natively as the first translation step. I, of course, wanted to play with this, so I came up with a small testing plan. This simple service DLL, and that's literally what it's called in this product, is a DLL I wanted to load and run some functions on it myself. And I'd use this reversed JavaScript client, the Electron client, to sort of get an idea of what the call flows would be, what the arguments would be, etc. Eventually, I end up in a POC, like extremely minified and significantly longer, that looks something like this. There's a function called simple launch user app process. It takes a few arguments, but the first three are interesting. And while running this, of course, using some Frida to get a sense of what the arguments look like, I realized that there's some paths that I can add. When I initially ran this, it didn't work, and it needed a little bit of tweaking to understand how those paths relate to each other. It's a little complex, but I suspect this is a security feature that they've implemented to try and make sure that code only runs from a specific folder. You see, parameter 1 needs to be a folder relative to this app data path, and parameter 2 needs to be relative to parameter 1. Anyways, what that really boils down to is if you want to make this call, you can give this common as an argument, which is a path relative to app data, and then assuming your payload lives there, give that argument to run. When you run that, the DLL would be extremely verbose in what it's doing, and one of the lines you might spot there is this one that says this PE file is not trusted. Now, I haven't been able to have I don't have a Razer Synapse code signing cert, so I'm fairly disappointed at this stage, until I realized, but actually the code signing is in that client DLL that I have complete control over. They're doing it correctly when verified trust is the way to do this, but I can simply patch that out, which is exactly what I did. Make a copy of simple service DLL, patch out the PE certificate validation, and rerun the POC. In this case now, while everything works, there's no error, I also don't have a user added, which is a fairly confusing thing. That was when I realized, actually, I've already had this trick where the side-by-side assembly manifest can get added to an EXE, and I needed this add user POC of mine to run in an elevated context. So doing exactly the same trick by having the mt.exe attach this manifest to my payload, I can get code execution the way I wanted it to be. So if we take a quick look at what the Razer Synapse privilege escalation would look like, it would be something like this. I first just check that the task is running, that Razer elevation service. I then double check that I don't have my Razer user yet, and I also can't add it. Once that is done, I run the what's now called Razer pwn over here, which will load my modified DLL with all the security checks patched out. And if you quickly see, there'll be a pop-up that shows a new user added to this machine. And we have LPE on our machine. I was building these slides for this talk when I'm talking to a colleague about this bug. And he effectively made my LPE a one-liner. The part that I haven't shown you yet that is actually the interface with Razer Elevation Service is a COM object. And I'm a few days into my reversing journey and getting a lot of fun, but I'm not really thinking very straight and actually not being successful with COM interfacing. We have a look at OLE view again, and we get this prog ID for the Razer Elevation Service. And my colleague shows me how to do the interaction with COM objects in PowerShell. The first thing you can do is instantiate a new object using the prog ID that you've enumerated, and then you can run get member on that to see which methods exist. You can already see where this is going. There's a launch process. You've got an option of 2, of which you just pass in a path and it would run that target for you in an elevated context. So you can ignore all this complicated patching and just use this one-liner to get LPE and Razer Synapse 4 unpatched. Okay, so let's wrap up quickly. I didn't only have success, there were definitely some failed attempts. I looked at a few targets, which included the HP support assist, Gigabyte Control Center, which has a very interesting architecture, and Lenovo Vantage. Just last month, Atreides Partners released a blog post where they also looked at Lenovo Vantage, but I think the researcher had more sleep than me, and they found some really cool bugs that I encourage you to have a look at. A whole bunch of registry things that I didn't know was possible. So have a look at that. In summary, the vulnerabilities that we've looked at included these 6 CVEs. They've all been reported and fixed. And Acer decided to make 2 bugs one, which I don't really understand, but that's fine. But like I said, they're all fixed. It leads me a little bit to talk about the disclosure for a bit. And if you are a vendor, please hear me out. In the case of Asus, I tried to disclose these vulnerabilities, but their disclosure page has a WAF, and it's blocking bad payloads. I'm sending them bad payloads. Please accept them so that you can have a look at the detail. So it made for a frustrating runaround to get that reported. On a more serious note, though, there was a research collision here where another researcher, 2 months after I reported, also reported similar bugs. In fact, the same original origin bypass. But instead of telling the researcher this has already been reported and worked on, they sent us the email with exactly the same CVE announcement. Except when you click on the email, the CVE is credited to me, effectively stringing this researcher along. I'm really sorry about that, Mr. Brew, but what's interesting, if you look at their blog, they have since hacked more Asus things, which I think is a little bit of a revenge hack and very funny to see. On the positive side, MSI responded incredibly fast. Like, the communication was clear, they were the first one to fix their bugs, etc. So that's definitely a win. From a Razer perspective, though, they used a bug bounty program which effectively fronted the security team. When I reached out trying to talk to someone to talk about this DEF CON talk, the CVE, etc., I couldn't believe how many tickets on an internal system ended up in my mailbox as they're sort of pushing this around. Who can I talk to? It unnecessarily delayed the process, I think, and I think the communication could be a little bit better there. I want to leave you with this idea of what I'm going to call the pwn triad. If you find a privileged service that has an RPC mechanism, be it a name pipe, COM object, TCP, whatever you think you're having, check if there's an authentication or a validation issue, which there probably is, and you will find a vulnerability. In fact, this could also just be a recipe for free CVEs. In conclusion, I think products built in 2025 doing silly RPC things like this is really unnecessary. In fact, if you think you need that bloatware, think twice. There's probably better resources to get that. And if you want to go CVE hunting, check what you have installed right now. And just before you uninstall them, maybe you can get a free bug. For all of these vulnerabilities, there's a bunch of POCs that I've put on GitHub. If you want to play with them, I think there's some more attack surface in many of these tools. You can get it in this QR code, which should be public after this talk. That's what I wanted to show you for bloatware hunting, vulnerability hunting. Thank you.